All right, let's talk about the group 1A elements for a few minutes here, and we'll just talk about some generalities about the group 1A elements. The first thing that you need to know about them is that they all have the same outer electron configuration, don't they? They all end with ns1. Okay, so they all have one valence electron in the s orbital. They all like to lose that one electron to become isoelectronic with the previous noble gas. Notice that this is n is greater than or equal to 2. So this doesn't apply, or not all of this applies for hydrogen, but they like to lose one electron to become plus one. And I've told you this already. They like to be plus one cations. Those metals in group 1A, the alkali metals, so alkali metals, they can react with water to give you a metal hydroxide and hydrogen. You might have seen the reaction of sodium with water, which causes a fire. Well, if you do try the same thing with potassium, which comes below sodium because we have lithium and then sodium and potassium, well, you know that valence electron, that 1s electron, is held less tightly by a potassium, and so it's even more reactive. So I wouldn't recommend dumping potassium in water. It's even more violent reaction. All of these metals also combine with oxygen to give you metal oxides. Here are some pictures of the group 1A elements. Most of them are soft metals. You can see sodium here, and I don't know if anybody's had a chance to, handle sodium before, but you see that the sodium is under a liquid, and that's definitely not water, is it? Because then it would react, but the sodium is actually stored under a mineral oil, and that prevents it from being exposed to water that's in the air. The same thing applies to potassium. This glass vial here, this is called an ampoule, and you simply crack this open, if you hold it in your hand and crack it with your thumb. And again, the same thing applies with potassium, in that it has to be kept away from moisture in the air. Otherwise, a violent reaction will ensue. The group 2A elements, they all have the same outer electron configuration, in that they all have two valence electrons in an s orbital. In terms of their reactivity with water, if you try to react beryllium with water, you actually get no reaction. Magnesium is a little more reactive. It will react with water, but it has to be water in the gaseous phase. And H2O in the gaseous phase, that's called steam. Okay, so magnesium will react with steam to give you a metal hydroxide plus hydrogen, whereas calcium, strontium, and barium will also react with water to give you a metal hydroxide, but this is at room temperature. Somewhat less reactive than the group 1A metals. Here are some pictures of the group 2A elements. And what do we notice about most metals? That they're dull or shiny gray solids. If we look at the group 3A elements, we have boron, which is a metalloid, and the rest are all metals: aluminum, gallium, indium, thallium. When aluminum reacts with oxygen, it forms aluminum oxide, and aluminum can also react with an acid. This is the net ionic equation shown right here for aluminum reacting. This is the reaction with hydrochloric acid. That aluminum gets oxidized to aluminum 3+, and hydrogen gas is liberated. Again, the group 3A elements are dull or shiny solids. Gallium is kind of an interesting metal in that it can melt in your hand. It has a very low melting point. It's still a solid at room temperature, but it can melt just with body heat. These are showing some representative reactions of tin and lead respectively with acids. Remember that acids liberate H+. You should be aware of that. And so both tin and lead can react with acids to give you tin 2 plus and lead 2 plus, plus they liberate hydrogen gas. It's also important to note that carbon in group 4A is a nonmetal. Silicon and germanium are metalloids, whereas tin and lead are metals. Here are some pictures of the elements in group 4A. You can see the two allotropes are two forms of carbon. We see a diamond, which you're all completely fully aware of, I'm sure. And then we have carbon graphite over here, which is kind of an interesting allotrope in that it's a good conductor of electricity, which might be counterintuitive to you because carbon is a nonmetal. And generally speaking, we don't think of nonmetals as being good conductors of electricity. The group 5A elements, I want to focus on nitrogen and phosphorus. When dinitrogen pentoxide or tetraphosphorus decoxide react with water, they form the important oxoacids, nitric acid, and phosphoric acid, two of the most important acids on the planet Earth. Nitrogen and phosphorus are nonmetals. Arsenic and antimony are metalloids, and bismuth is a metal. You can see that nitrogen, again, which is a nonmetal, is a liquid. And when we get to phosphorus, which is also a nonmetal, it's a brittle solid. And then antimony and arsenic are here, and then bismuth is a metal. The group 6A elements, the most important sulfur-containing compound in terms of this planet is sulfuric acid. So you shouldn't leave general chemistry without knowing how sulfuric acid is produced. And it's produced by the reaction of sulfur trioxide with water. Oxygen, sulfur, and selenium are nonmetals. Tellurium is a metalloid. Polonium is radioactive. Another thing that's interesting are the molecular formulas for oxygen, sulfur, and selenium. I'm sure you're all aware that oxygen is O2. It's a diatomic element I asked you to memorize a long time ago. Sulfur in nature is actually S8 when it's found by itself. Normally we just write it as S in an equation. And selenium is also Se with the subscript 8. The group 7A elements are the halogens. So fluorine, chlorine, bromine, and iodine are the halogens. Astatine is radioactive. These elements have high electron affinities, and they have high ionization energies. They all like to gain an electron to become isoelectronic with a noble gas, and the halogens will all react with hydrogen to give you a hydroacid. So hydrofluoric acid, a hydrohalide. So hydrogen fluoride, hydrogen chloride, hydrogen bromide, or hydrogen iodide. Again, as we go down a period, or down a group rather, you can see that we go from chlorine, which is a gas, to bromine, which is a liquid, and then finally to iodine, which is a solid. The group 8A elements, these are the noble gases. They have completely filled S and P subshells. They have extremely high ionization energies. They have no desire to take on extra electrons because their valence shells are full. There are no known compounds made with helium, neon, and argon. There are a few compounds known with xenon and a couple of compounds, a few krypton compounds have been prepared. I'm not going to ask you anything about those. Really, the last concept that I need you to know from this chapter deals with oxides from a period. We looked at metal oxides and non-metal oxides. What you need to understand is that when you take those oxides and look at their behavior, as we look at their nature as being an acid or a base, as we go from metal oxides to non-metal oxides, their behavior goes from basic to acidic. And so if you were to compare these oxides in this example, it says classify these oxides as basic, acidic, or amphoteric. Remember what I just told you, that as we go across the period like this, we go from basic oxides to acidic oxides. And therefore, rubidium oxide, since it's on the far left, this is going to form, or this is a basic oxide, as is beryllium oxide. It's also a basic oxide. And since arsenic is over on the in group 5A, which is on the right-hand side of the periodic table, it's going to form an acidic oxide.